Now we're going to talk about flow integrals as well as circulation. We have two vector fields here that we could consider. This first vector field, for instance, gives us an idea of zero circulation around that unit circle plane, whereas the second figure that we're looking at has a non-zero circulation. You can see we have this circular pattern occurring here. So if we have these velocity fields, they could represent, say, fluid moving through a region in space. More specifically, like a turbine chamber of a hydroelectric generator. Flow could be air, it could be fluid, it could even be electricity. Okay, so we're talking about the flow and circulation. So as we can see, we have our definition here for flow, and it's basically the same definition as our work definition. It's the line integral of the force field dotted with the unit tangent vector integrated with respect to arc length. So this is called the flow integral. And if a curve starts and ends at that same point such that A is equal to B, the flow is called the circulation around the curve. So if we went from 0 to 2 pi, starting and ending at the same point, that would give us the circulation. So this tells us, this line integral that we've been learning about and using tells us about flow as well as the circulation. One concept that we really want to keep in mind, and we've kind of touched on this in our notes, but it's that the direction along our path C matters. If you want to reverse or figure out how to reverse that, the direction of your circulation or your flow, if you negate or you find the opposite of that unit tangent vector, then the integral sign changes, and that's going to be evaluating the flow in the opposite direction. So let's just do a quick example. In this example, we're given a force field. F equals x minus y times the I vector plus x times the j vector. We're asked to find the circulation of the field around this circle parametrized by cosine ti plus sine tj, which just represents a circle of radius 1, from t equals 0 to 2 pi. Now, t equals 0 to 2 pi, that means my initial and terminal point, and we're starting at 0, we're ending at 2 pi, initial and terminal point are the same. Because of that, we're not just finding the flow, we are finding the circulation. So this problem is going to work out the same way all of the line integral problems that we have worked on in this section also worked out. We're going to need to do a couple of things. We're going to plug in our parametric components into my force field. We are going to take the derivative of r. Then we are going to dot that derivative with the force field, calculating then the integral from 0 to 2 pi. So when I plug x equals cosine t, sine t equals y, and then that cosine t equals x in, this is my result. So I'm going to dot this then with the derivative of r of t. My derivative of cosine gives me negative sine t. My derivative of sine in r gives me cosine t. So I have negative sine t I plus cosine t j. So now let's dot each of these, which is just the product of each component summed together. That dot product is going to be negative sine t times cosine t minus sine t, and then cosine t times cosine t, which is cosine t squared. When I distribute, I end up with a sine squared plus cosine squared, which gives me 1 minus that first distribution or product. We have 1 minus sine t cosine t. Now, we just need to evaluate our integral from t equals 0 to 2 pi. Now, my flow integral, as defined in our text, but is going to be the integral from 0 to 2 pi of f dotted with the derivative of r with respect to t, integrated with respect to t. And that gives me t minus, and we can integrate this using a u substitution. We get 1/2 sine squared t, plugging in 2 pi and 0. This will give us our flow. And since the initial and terminal points, since it stops in the same place it starts, this flow represents the circulation all the way around that circle. So plugging those values in and simplifying, we find that the circulation is 2 pi. And here you see my red vector field representing what we started with, and my unit circle that we have been traveling along. That's my path. So I found the flow along this path. And so that is how flow and circulation relate. And essentially it's that same line integral definition. So hopefully this makes sense. You guys are good to go. As always, email, comment, questions, anything of concern. I'm here to help you. Have a great day.